Hello. In this video, we will talk about similarity. Before we begin, I would like to ask you some questions to see whether you have the answer to these questions. First, what are the conditions for complete similarity in dimensional analysis problems? Second, can we test the airflow properties around an object in liquid? Third, what are the pros and cons when a model larger than its prototype is used? If at this moment you cannot answer all these three questions, it's alright. And that's the purpose of this part of the video. And at the end of the video, you should be able to answer all these questions correctly. First, let's look at some real-life example of how people perform experimental testing to study the flow around some objects. The one on the top is the bicycle model with a cyclist in the wind tunnels test section. As you can see in this example, the model is of real size. The second example is the F1 vehicle model in a wind tunnel, and as you can see, these two are real drivers, so meaning that the F1 model is of smaller scales compared to the real F1 car. And the last one at the bottom is this RoboFly, which is a robot model to simulate the flow around the wings of fruit fly. The adult fruit fly is only about 2.5 mm long. So this RoboFly is 100 times larger than the real fruit fly. And the fluid used is not air, but is oil. We know that fruit fly does not swim in the oil, so meaning that it is okay to use liquid instead of air, although the real object is subjected to airflow. So from these pictures, you can tell that the model can be the same size with the real object, we call prototype, or it can be smaller or larger than the prototype. Experimental approach is needed when a problem cannot be solved using analytical or numerical methods. Often, scale models are used for reasons like save cost, easier to analyze the flow, and so on. For example, it is possible to study the flow around a car using a smaller model instead of the full-size vehicle. There can be some reason why we didn't use the full-size vehicle. For example, the test facility is too small to fix in the real vehicle, so using a model will be convenient. What are the conditions required to ensure that the result obtained from the small-scale model is applicable to the real one? In general, there are three necessary conditions for complete similarity between a model and a prototype. We call this the geometric similarity, kinematic similarity, and dynamic similarity. Geometric similarity is when a model has the same shape with a prototype, although it can be scaled by some constant scale factor, which means the model must look the same as the prototype, although it can be smaller or larger. The next, kinematic similarity, which is the velocity at any point in the model mass proportional to the velocity at the corresponding point in the prototype flow. And third, the dynamic similarity, which is when all forces in the model flow scale by a constant factor to corresponding forces in the prototype, or we call this force scale equivalence. In a general flow field, complete similarity between a model and prototype is achieved only when these geometric, kinematic, and dynamic similarity are achieved. Now, in dimensional analysis problem, we often have one pi, which we call dependent pi, and we use a notation pi 1 to indicate it's a dependent pi. And parameter pi 1 is a function of several other pi's, which we call independent pi's. The functional relationship between the dependent pi and independent pi's are written as this. Pi 1 equals to a function of pi 2, pi 3, and so on. To ensure complete similarity, the model and prototype must be geometrically similar, and all independent groups must match between the model and prototype. Or we can write, for dimensional analysis problem, if the independent pi's are matched between model and prototypes, which is if pi 2 of model matches the pi 2 of prototypes, and pi 3 model matches the pi 3 prototypes, and so on until the pi k model matches the pi k prototypes. Then the dependent pi 1 of model will match the pi 1 of prototype. Let's look at one example. We were to establish a functional relationship between the aerodynamic drag and other dimensionless parameters, meaning that, let's say the aerodynamic force acting on the car, Fd, is a function of the velocity, the length, the density of the fluid, and the dynamic viscosity of the fluid. Then we can write the functional relationship. Then for this problem, we have two pi groups, which is pi 1 is the force coefficient. It's a function of pi 2. And pi 1 is the force divided by density, velocity square, and length square. And pi 2 is equals to rho VL per mu, which is the Reynolds number. So for this problem, in order to achieve complete similarity, we need to match all the independent pi groups, which is in this case only pi 2. So if pi 2 of the model matches the pi 2 of the prototype, then pi 1 of model will match the pi 1 prototype. So this is the condition to achieve complete similarity. Based on the condition required for achieving the complete similarity between model and prototype here, it means that to achieve a complete similarity, we only need to match pi 2 model with the prototype. And pi 2 is the Reynolds number, which is rho V L per mu. Model equals to rho V L prototype. So we only need to adjust the density, dynamic viscosity, or the velocity and the length of the model so that the Reynolds number would match between the model and prototypes. And based on this equation, it does not say that the density has to be water or air. We can use water, which is of higher density, and use a smaller length for the model to achieve the value here. Or we can use air density, meaning that we test the model in air, while we use a larger model to balance out the smaller density in order to achieve the same Reynolds number of the prototype. So the type of fluid used is irrelevant. It can be liquid or it can be air or other gaseous. Also, if the density and viscosity is the same between model and prototype, then we can manipulate this by using a higher test speed for a smaller scale model, or use a smaller testing speed if we can use a larger model. And if this is achieved, then we have a complete similarity, which is the force coefficient for the model will match the force coefficient of the prototype. So once we determine the force in the wind tunnel, then we can use this to estimate the force on the prototype by simply calculating the FD of the prototypes. So, knowing all the ratio of these, and once we determine the force of the model, then we can predict the aerodynamic force on the prototypes. Thank you.